All right, lecture 22. So this one is more on using the work-energy theorem that we derived in the previous lecture. So just to recap, the work-energy theorem says that the change in the kinetic energy of an object is the result of work being done on the object, or work we defined as a force being applied over a displacement. The object has to be moving and the force has to be working in the direction of, either parallel or anti-parallel of that displacement to do work on the object. There were a couple things that were introduced, like doing the work, or calculating work rather, involves evaluating the work integral, which involves this vector dr. This is an example, by the way, of what's called a path integral, where you're not integrating over a surface, but instead you're integrating along a path where the path itself could be multidimensional. So the displacement vector is more or less, you can think of it as just a little vector that is constantly pointing in the direction that the box is moving. So it is always going to be parallel to the velocity vector, but you can always just write it as dx, dy, dz if in 3 dimensions. If it is a 2-dimensional vector, just dx comma dy. And then if you know something about how the object is moving, for example, if it's only moving horizontal or only moving vertically, you can set the dx or the dy equal to 0 to correspond to that. You actually don't need to actually do that. You could just evaluate, because your limit, another way you could do it is to always keep it as dx, dy, dz, but then when you do the integral, your limits of integration will work into it the fact that an object is only moving horizontal or vertical, but I wouldn't worry too much about that. Let's see, so again, work results in changes in motion. An object speeds up or slows down when forces act on that object in a way that they work in the direction of motion or they work in the opposite direction of motion. In that case, it would be slowing down. Something I will state that ties back to a result that you might have seen if you took physics in high school, and we saw this with an example that we did in the previous lecture. If the force that you're using happens to be a constant force, an example of this might be the gravitational force near the Earth, where that force is usually 0, comma, minus g. It is a constant in the vertical direction. Then the work that is done by that particular force, you're evaluating this integral. That integral, if the force is a constant force, you can take, like a constant, just a number, you can take it out of the integral, and this is just the same as the force dotted with the integral of the displacement vector. But then that integral is then just, you're integrating what is the total change that the object undergoes. So that ends up just being the same thing as force dotted with the distance, or force times distance. And then you also have to take into account the fact that the force might not be pointing in the exact same direction as the distance, so you have to work in the cosine theta term as well. All right. So let's see. What else do I need to say before we get into the new stuff? Right. So something, a general result in this case is, if the network is positive, that means the kinetic energy increases with time. And if the work is negative, then the kinetic energy is decreasing from point A to point B. And then if work is 0, there is no change in the kinetic energy. If it is moving at a speed, it will continue to move at that speed. And now with work energy, work and energy are a little bit more abstract. So you might wonder, we've learned about when objects speed up or slow down or simply change direction and move at a constant speed when we did Newton's laws, and we should be able to convince ourselves that this is saying the same thing. So let us just quickly review what we did when we were looking at Newton's laws of motion. In this case, let's take case 1, where I have some velocity vector v, and then I had some acceleration vector that points generally in the same direction. It might not be exactly the same direction, but it is closer to being parallel to v than it is to being perpendicular or anti-parallel. Now we know now that accelerations are the result of forces. So if there's an acceleration in one direction, that means it is likely the result of a net force in the same direction, since they are related just by a constant m. And we saw this when we looked at, when we did vector analysis, that since these two vectors are pointing in the same direction, this resulted in an object speeding up. Now, does the work-energy theorem say the same thing? Again, work energy is you're evaluating the force dotted with the displacement, where I said this guy is parallel to the velocity vector. Again, that's the result of dr equals v dt. So the displacement vector is parallel to the velocity vector. And again, remember, this is the same thing as the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between the two. But then, given what I just wrote up top, that is the same thing, being sloppy here, as the same thing as the magnitude of the force vector times the magnitude of the velocity vector times some little amount times dt times the cosine of the angle between the two. So again, this is the theta between f and v. And so in this case, if the two vectors are close to being parallel to one another, theta is less than 90 degrees. In this case, this is positive by construction, this is positive by construction. We saw in the previous lecture that meant the cosine is a positive number as well. And so this entire integral is greater than 0. So as a result, work in this case is positive, which by the work-energy theorem says that the kinetic energy then increases. And notice that matches our idea of what we would expect just looking at forces. Since they are almost parallel to one another, or they point generally in the same direction, that results in the object speeding up. Again, and if you don't remember where that came from, remember that you can always decompose the acceleration vector into a part that is perpendicular to v and a part that is parallel to v. And since it has that part parallel to v and they're pointing in the same direction, that results in it speeding up. And then this part here, the perpendicular part, results in it changing direction. And so you can convince yourself, in the case where you have a velocity vector, but then you have an acceleration vector that maybe points in this direction, that as a result, this is a case where the object is slowing down. But since the acceleration can be thought of as a force, in this case, the velocity vector is pointing in this direction, the force is pointing in this direction, the angle between the two is greater than 90 degrees. As a result, the cosine of the angle between the two is negative. As a result, the work you get when you evaluate the integral f dot dr is then going to be negative. And we see in that case, by the work-energy theorem, that means that the kinetic energy change is less than 0, or the object slows down. And notice how that jives with what we discussed when we talked about forces and Newton's laws. Then finally, the third case, if you have a velocity vector, and then you have an acceleration vector, or equivalently a force vector, that is perpendicular. Excuse me. We talked about how this is a case where the velocity does not change in magnitude, but it does change in direction, for example, circular motion. But then also notice that in the case of evaluating the work integral, f dot dr, the cosine in this case is 90 degrees, and the cosine of 90 degrees is identically 0. So then the work in this case is 0, which means that the change in kinetic energy is 0. The object does not speed up or slow down. In this case, it simply changes direction. But remember, the gains that we get from using work energy, which will simplify a lot of problems down the road, the thing that we lose is we don't learn anything about the vector directionality of anything. Energy is a scalar. So we do not know we don't know in what direction the velocity is changing. But we just know that the magnitude of the vector is not changing. All right, let's see. What should we do first? Let me pull from my lecture notes. Yeah, and also just to go back to the example we did, when we had the box that was being pushed horizontally. You could also have asked, why did we not have to worry about anything in the vertical direction? In this case, the box was moving horizontally to the right, but gravity is, so then this dotted thing here, you can think is connected to the displacement vector. Each one of those dots you can think of as a little vector that points in the direction the object is moving. But then the force of gravity, in this case, is pointing straight downward, and since they are perpendicular to one another, the gravitational force, while it is always acting on the object, the object is always being pulled down by the force of gravity. In this case, the force of gravity does no work on the object. The fact that the object is speeding up as I push it across the horizontal table has nothing to do with gravity, which I think jives with what your intuition says, but now we can see mathematically that is borne out as well. And then similarly, for the contact force of the table, it's similarly, since it's perpendicular to the direction the box is moving, the normal force also does no work. You might have thought that, they don't matter because they cancel each other out, and that is actually true in this case as well. If they did do any work, they would end up canceling each other out since they are anti-parallel to one another. But in this case, it's not the fact that they cancel each other out. It's, in this case, the fact that they are just simply perpendicular to the direction that the object is moving. All right. I'm going to clear this away. So now let us study in detail a particular problem that will allow us some practice using the work-energy theorem, and then we'll also reveal some interesting information about certain kinds of forces and how they transfer and transform energy. So let's do the case of I have a ball that has a mass of 0.1 kilograms or 100 grams. I initially release the ball with a speed of 10 meters per second. Vertically upward, it rises into the air, reaches its highest point, and then falls back down to the ground. And I drew it with a slight horizontal motion, but that's just so we can easily see the path. Actually what would happen was it would rise straight upward, come to a stop, and then travel back down and fall back into my hand. Let us define our coordinate system. I will call this the horizontal direction, which won't matter because there's no horizontal motion. And then the vertical direction, and I will define up as positive. Now, I could ask a question like, how high does the ball go? If it starts at where, you can see I put my origin where the ball is released, so it starts at a height of 0, it reaches some height h, I could ask, what is h? This, again, is something we could easily do with Newton's laws, and we could use Newton's laws and see that when we do it with work, we get the same answer. So let's, again, just run through. I don't know if I did this in class, but let's just do it again and run through an example using Newton's laws, and then we'll see when we do work energy, we get the same answer. Let's see, so what do we need to know? We know that the acceleration is downward and it's just minus g. which, just so the math is nicer, I'm going to round and call g 10 meters per second squared instead of 9.8. So then I know that since the acceleration is constant, the final height equals the initial height plus the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times t squared. So I know in this case I'm looking for h. It starts at 0. It started with it started moving at 10 meters per second squared times some time, then minus 1/2 g t squared. I want to know h, but it involves this t, which I do not know. Worry not, because I know the other kinematic equation, that the final velocity equals the initial velocity plus the acceleration times time. And I know at its highest point, it is not moving in the vertical direction. It's not moving in the horizontal direction either in this case. So the final velocity is 0 equals the initial velocity of 10 meters per second minus g times t, or that the amount of time it takes to get to the highest point is 10 meters per second divided by g. If I say this is 10 meters per second and I round g to 10, this is then 1 second. Then I can plug that in to this guy, so then this is 10 meters per second times 1 second minus 1/2 10 meters per second squared times 1 squared. That is 10 minus 5, or 5 meters. So it rises to a maximum height of 5 meters. Now let's do it again using work energy. So in this case, again, the only force is gravity, which I'll write as a vector as 0, minus g. The displacement is only in the vertical direction, so I'll write that as 0, dy. In this case, let's see, then the dot product of the two is minus mg dy. In this case, since the force is a constant, I could have also used the expression that the force times the total displacement is the same. We will again, this was another example that shows you where that comes from. So then the work from gravity is the integral of f dot dr, but I said that is the same thing as minus mg dy. That is the same thing as minus mg, the integral of dy. That is the same thing as minus mg delta y. In this case, the final height was h, the initial height was 0, so this is minus mg h minus 0, or just minus mg h. So the work that is done by gravity is negative mgh. H, we know, h in this case, had we not done Newton's laws, we would not know the number for h, but we know it's going to be a positive number, so we know this entire expression is less than 0. And we should get in the habit of making sure that that makes sense physically. Mathematics is one thing, but these have there's physical meaning behind what we're doing here. Since this is less than 0, we know by the work-energy theorem that means that the kinetic energy is decreasing. Gravity is sapping away or taking away kinetic energy from the ball. And that should jive with our intuition of what happens when I throw a ball up in the air. It slows down more and more and more until it comes to a stop at its highest height. So then the change in kinetic energy equals minus mgh. In this case, it is the final kinetic energy minus the initial kinetic energy equals minus mgh. The final kinetic energy is 0 because it has 0 velocity at its highest point. So then this says negative 1/2 m, the initial velocity squared, equals negative mgh. M's cancel, the negatives cancel. So then it looks like I get v squared over 2 equals gh, or h equals v squared over 2g. V squared is 100 over 2 times 10. 100 divided by 10 is 10, divided by 2 is 5 meters. So that's good. We did 2 different ways and we got the same answer. It would have been very concerning had that not been true. Now we could also ask ourselves, how much kinetic energy did the ball have when it left my hand? How much kinetic energy does the ball have when it reaches its highest point? And how much work was done by gravity as the ball rose from my hand to the highest point? So the initial kinetic energy, 1/2, and I said this was 0.1 kilograms, which is a tenth, times 10 meters per second, and that's being squared. And you can convince yourself that is 5. The units of energy is joules. So the ball started with 5 joules of kinetic energy. The final kinetic energy in this case, since it was at rest at the top, is just 0 joules. Now you could ask, how much work did gravity do? That was minus mgh, or minus 1/10 times 10 times 5. Notice that is minus 5 joules. Curious. Maybe this isn't too surprising. The ball had 5 joules worth of energy. It came to rest at its highest point, so that 5 joules of energy had to go somewhere. Where did it go? It got sucked away from gravity. Gravity sucked it away and took away by doing negative 5 joules of work on the object. So as a result, the final kinetic energy of the object is 0. Again, if I were to write it out using the work-energy theorem, since delta K equals the work done, delta K is just the final kinetic energy minus the initial kinetic energy equals the work done, in this case by gravity. Or that the final kinetic energy is the initial kinetic energy plus the work done by gravity. This was 5, this was negative 5, which makes this guy 0. Energy really is just an accounting problem. You started with 5 joules of energy. 5 joules of energy got taken away by gravity, so as a result you have 0 joules of energy left. Like thinking of our analogy from 2 lectures ago, I have $5, I put $5 away, as a result I no longer have any money on me. Energy is just really an accounting problem. Alright, so I think that takes care of that page. Now let us do the example. Let's continue with this, but now let's do the second half of the journey for the ball. So let me redraw it real quick. So if it came up, I have this dotted thing, I don't know why I'm not using it. Oops. It comes up, comes back down. Now let's actually do the second leg of the journey, where it starts here and ends here. So it starts at rest at its highest point, falls back down to my hand over a height of 5 meters. What can we say about the work that gravity does in that case, and how much does the kinetic energy of the ball change? So in this case, we could also use Newton's laws, but I'm sick of doing that, so let's just go right into the work-energy theorem. So we could redo everything we did before. Again, gravity is 0, minus mg. dr is just 0 dy. There's only motion in the y direction. the dot product in this case is again minus mg dy. Yet again, the work due to gravity is this integral, which is going to yet again give me minus mg big delta y, or the total, not displacement. Again, I could have also used, since the force of gravity in this case is a constant, I could have used this expression, which is just then the magnitude of the gravitational force times the magnitude of the net displacement times the cosine of the angle between the two. But in this case, gravity and the direction that the object is moving is in the same direction, so cosine is just 1. So this just becomes unity, and we'll get the same answer. Spurious little thing here. There we go. In this case, delta y is the final position minus the initial position. In this case, the final position is 0, and the initial position was h. So then we get mgh. I could actually even be more specific. We get plus mgh. Or the work done by gravity in this case is plus 5 joules. Previously it was minus 5 joules, now in this case it's plus 5 joules. So the work done by gravity in this case is positive. So we should expect by the work-energy theorem that the change in kinetic energy then is going to be positive. Our intuition should say that that is indeed true. As the ball starts from rest at the top and falls back down to my hand, we know that the ball speeds up while it does that. So then if I actually write it out, change in kinetic energy in this case is a result of the work being done, as 1/2 m final velocity squared minus 1/2 m the initial velocity squared equals the work done by gravity, which in this case was plus mgh. The ball in this case started at rest, so that term goes away. And as a result, it is 1/2 m final velocity squared equals mgh. This is the same expression before, just there are no negative signs in this case. So the answer is going to be the same, and you will get the final velocity is 10 meters per second. The same velocity that it had when it left my hand. So in this case, I threw the ball up at 10 meters per second. Gravity did work on the object, which sapped away the kinetic energy of the ball because the work was negative as the ball rose up into the air. Eventually, it had no kinetic energy left. Gravity then started to do positive work on the ball, and the ball started to return back to my hand as it fell down. It accelerated. We know from Newton's laws. Work-energy theorem is saying that the gravitational force is doing work on the ball, and so that the ball then is speeding up as it moves or is displaced in the vertical direction. And by the time it returns back to my hand, it has regained its velocity and now is back at 10 meters per second. Again, thinking of Newton's laws, perhaps this is not too surprising because we know when we did projectile motion that there is symmetry in the trajectory when the ball is going up and when the ball is going down. So the fact that it's symmetric also could have we could have used that to convince ourselves that the final velocity should be the same as the initial velocity. But in this particular case, it seems like if we were to draw this as a graph, let's see, and this is energy. Actually, I'm going to do it this way. This is energy. Initially the ball had 5 joules of kinetic energy. Gravity did minus 5 joules of work. As a result, the kinetic energy of the ball ended up being 0 when it reached its highest point, or it was at rest. And then in the case of the ball returning back down to my hand, it started with 0 joules of energy. Gravity then did 5 joules of positive work. So as a result, the kinetic energy, once it returned back to my hand, had returned back to 5 joules of energy. And so again, we're really just thinking of this as accounting. As long as we account for what is holding the energy and where the energy is going or being transferred to and from, we can say something about what is happening at the initial point and at the ending point just by looking at the energy. Now let's look at the same problem, but I'm going to add a slight twist. So suppose now I throw the ball up into the air. It reaches a maximum height of 5 meters. But as soon as it reaches a maximum height of 5 meters, I slide a 5-meter ramp right under the ball, and then the ball, rather than falling back down in a straight line, rolls down a ramp to get back to the ground. So again, this is 5 meters tall. So I throw the ball vertically upward, but instead of it falling vertically back downward, I quickly slide a ramp underneath the ball so that the ball takes a different path as it travels back down to the ground. And we could ask ourselves, when the ball returns to the ground or back to its original height, I guess I've drawn the height slightly differently here. So when the ball returns back to its original height, what is the kinetic energy of the ball? What is the final velocity of the ball? How much work is being done by gravity in this case? When there is a ramp that is changing the path that the ball is taking. It's not just falling vertically in this case, now it is falling at an angle. And in class I did the example of, I assumed that this angle here was 45 degrees. And it has a height of 5 meters. All right, so the upward trajectory is the same. It starts with 10 meters per second velocity. It rises up to a height of 5 meters. Gravity did, in that case, negative 5 joules of work, which took away then the 5 joules of kinetic energy that the ball had. The ball is then at rest at the top. Now it's sliding back down the ramp. Now again, we could use Newton's laws to solve this problem, but I'd rather not. I'd rather get some practice using work energy. So let us use the work-energy theorem, and actually let us solve this in 2 different ways using the work-energy theorem. So let's see. The first way is I know I can always start super general. The change in kinetic energy is the result of the work that is done on the object. So if I can calculate the work that gravity does as it rolls down the ramp, I can calculate the change in kinetic energy. So in this case, the ball is starting up here and it's rolling down at an angle versus gravity, which is pointing straight down. So the path that the object is taking, there's an angle between gravity and the path that the object is taking. If this represents dr, and this represents the force of gravity, this angle happens to be 45 degrees, also in this case. In this case then, if Fg is, or rather actually, let me erase this. If I want to evaluate the dot product, I'm going to go back down here to the integral. The dot product then is the magnitude of the force of gravity times the magnitude of the displacement vector times the cosine of the angle between the two, which is 45 degrees. This is the same thing as mg, again not minus mg because it's the magnitude. Magnitudes are positive by construction, times, I'll call it dl, so this will just be along the ramp times the cosine of 45 degrees, which is 1 over the square root of 2. So then this just becomes, let's see, what can come out? The m, the g, square root of 2 can come out, then it's just the integral of dl along the ramp. So then this is just mg square root of 2 times the length of the ramp. Notice since it's going down a ramp, the path that it takes to get all the way back down to the ground is longer in this case than it was when it just fell vertically. So L ramp is longer than 5 meters in this case. Luckily, it's pretty straightforward to figure out what this length is. I made it easier on myself that if this is 5 meters, since this is 45, this is also 45 since this is 90. The angles have to add up to 180. By symmetry, this is also then 5 meters. As a result, this is the square root of 50, just by the Pythagorean theorem, or 2 square root of 5. No, that's wrong, sorry. 5 square root of 2. So the length of the ramp in this case is not 5 meters, but it's 5 times the square root of 2 meters. So then the work that is done by gravity is mg over the square root of 2 times the length of the ramp, which we just said by the Pythagorean theorem is 5 square root of 2. That's nice, the square root of 2 cancel. You again get mg times 5 meters, which is again 5 joules. It seems to be the exact same amount of work was done by gravity. In the case where it fell vertically downward, it did 5 joules of positive work. In this case where it went down a ramp, it also did 5 joules of positive work. So as a result of the kinetic energy theorem, since the change in kinetic energy in this case is equal to the work done by gravity, which is yet again 5 joules, nothing's going to change in the math. That says the final velocity of the ball is once again going to be 10 meters per second. Even though we're going down the ramp, and it will take longer for the ball to get to the ground, because it has to take a longer path, it will still achieve the same speed of 10 meters per second when it reaches the ground. Now that's interesting. Why should that be the case? Well, it might help if we do it another way. That makes it a little bit more obvious, I think, why any motion in the horizontal direction, the fact that the ball still went down 5 meters. It started at 5 meters above the ground, it went down to 0 meters. The vertical displacement was still 5 meters. But in this case, there also was a horizontal displacement of, since it's a 45, 90 degree triangle, also 5 meters. But that horizontal displacement ended up not mattering. Here we can see why. Remember, there are 2 ways I can evaluate the dot product. So the force of gravity is only in the vertical direction. In this case, the displacement is both and in the x and the y direction. There is horizontal motion and vertical motion. But notice when I take the dot product, since I multiply these 2 parts together and then add them to the product of these 2 guys, this is just minus mg dy, since in this case the 0 negates what's going on in the horizontal direction. So notice that since gravity is vertical, this is saying that work from gravity only cares about the vertical displacement. Since it is minus mg dy, when we actually evaluate the work by doing the integral, notice that this looks exactly the same as it did when the ball was just moving vertically. So again, it's just going to be mg delta y. And since in the vertical direction it moves down 5 meters, this then just becomes mgh, or plus 5 joules. So again, since gravity is pointing downward, you could think of this, I don't think I said this in class, but you can think of this as, when we did the dot product, we said that the dot product was a way, let me go to the screen. The dot product we said was a way where if I have two vectors, let me call it f, and then we have another vector, I'll call it r, that the dot product was a way for us to figure out the component of the vector that points in the same direction as r in this case. This we could call f along r. And we showed that that is the same thing as f dotted with r, oops, I'm anticipating where we're going with this, over the magnitude of r, just by the definition of the dot product. Because remember, when we did vector analysis, we said this is the same thing as f cosine of theta, if this guy is theta. But by the rules of the dot product, this is the same thing as that. So just to emphasize this again, f dot r is the same thing as the magnitude of f times the magnitude of r times the cosine of theta, the angle between the two. But I can be clever with my parentheses and write this as f cosine of theta times the magnitude of r, where you can think of this as the part of f along r multiplied by r. But you can also think of this as f times the magnitude of r times cosine of theta. So you could think of this as the part of r along f. So in the case of what we were doing back here, oh, I thought I could go back to a previous slide, but apparently not. That's a shame. This is imperfect software. So in the case where we had a ball going down a ramp and we had gravity pointing downward, one way of thinking about it is that there's a part of the gravity vector that points in the same direction as the displacement. You could also think of, if work is done by a force, and this force in this case is pointing downward, then the displacement, the work can only be done if there is a part of that displacement that points in the same direction as that force. So in this case, then it's only the vertical motion that is necessary for gravity to do work on the object. Also similar, you remember when we had the box on the table. In the box on the table, even though gravity was pointing downward, there was no vertical motion for the box. So, thinking about it this way, there was no component along F that points in the same direction as the displacement. So as a result, gravity did not work. All right. End of aside. Oh, now I can get it back? What the hell? Yeah, whatever. Right, so we had the case of we have a person, he threw the ball up, then the ball was moved onto a ramp, and then it came down. And in that case, that seemed to be identical in terms of energy to the case where the ball was thrown up into the air and then fell vertically back downward. In both cases, the amount of work that gravity did on the return when it came from the top to the bottom was equal to plus 5 joules. Then I gave an example for you to think about in groups in lecture where now let's do the same case where the ball throws up vertically, but then instead of a 45-degree ramp, I do one that is much more shallower, where it's still, there's a distance of 5 meters in height, but now it must travel along a very long path in order to get to the bottom. So the ball will take much longer to get to the bottom, but you can still convince yourself in this case the work that gravity does on its return trip is still just 5 joules. Again, because the vertical displacement in all of these cases is still the same. It still goes 5 meters down. And then I gave one final example of what if you threw the ball onto a ramp, but the ramp looked something like this. So there was a part where the ball went a little bit down, but then it moved horizontally, and then it went down again. In this case, gravity still does 5 joules of work. The kinetic energy of the ball is still 5 joules at the end. In every case, the final velocity is still 10 meters per second. Though again, just to re-emphasize the fact that energy is a scalar, not a vector, notice that in all these cases we can easily calculate that the final velocity of the ball is 10 meters per second, but in this case the velocity vector is pointing in this direction, in this case the velocity vector is pointing straight downward, in this case it's pointing in this direction, in this it's much more steeper, closer to vertical. In all 4 cases that are drawn here, the velocity vector points in a different direction, but we don't learn that information from energy because energy is a scalar. We only know that the magnitude of all 4 of these red vectors that I've drawn have the same length of 10 meters per second. Okay. Let's see. Oh my gosh, how are we already at 47 minutes? So what is interesting, gravity seems to be an interesting force in that as the ball returns back to its original position, what gravity took away during the upward path as the ball rose into the air and gravity did minus 5 joules of work, it gave that 5 joules back when the ball returned back to its original height. That is different than, say, friction, where if I were to push a box across the table, friction would do negative work on the object because the object is slowing down. But in the case of friction, there's no way for me to get that energy back. I cannot, say, push the box in the opposite direction and have friction give back the energy that it took away. And let's see, let me just sketch that out before I do springs. In the case of a box, if the box is moving in this direction, then we know that friction, since it opposes motion, friction in this case kinetic friction, is pointing in the opposite direction. If I were to evaluate work, force.dr, notice that these 2 vectors are, also remember this is in the same direction as the displacement. F.dr in this case is going to be less than 0. Work is going to be negative in the case of the box. So then, similarly, when I push the box in the opposite direction, friction is still opposing motion, so it still points in the opposite direction. Even though we're going backwards to our original spot, the amount of work that's being done is still less than 0. So when I do the integral, it's still going to be negative. Unlike gravity, where when it reversed its path, the work changed sign, and whatever energy was taken away was given back. Springs are similar in that what they take away, they give back, like gravity. So suppose I have a spring, I have a box that is coasting along a frictionless table. It will hit the spring, and then the spring will compress, and as it compresses, it will push back on the box, and eventually the box will come to rest. Remember when we did spring forces, we said that the spring force is K times the amount that the spring is squished or stretched. So this is the amount of squish or stretch. And I made a comment that you should be careful. So this is because when you use this expression for the spring force, what you're really saying is that the origin, in this case the horizontal location of x equals 0, that the location of the origin is at the same place as when the spring is neither stretched nor pulled. So that the equilibrium position of the spring is at the same place as the origin. Sometimes you might see this written like this, or I could write it as x minus x naught, where in this case, this is the equilibrium position. And then this is the, your current position. So just to draw an example of what that might be, what I might mean by that, if I have a spring that is currently being squished, where let's see, let me write it in two different ways. Where in this top example, this is the if this is right when the box first comes in contact with the spring, that is the equilibrium position, where noticed, afterwards the spring is compressed a little bit and everything has moved a little bit to the right. If I called this location the origin, that is where x equals 0, then this would apply just fine. But if I wanted to say, call this the origin and say this is where x equals 0, then I might use this guy right here and call this the location x naught, so that when the box gets compressed a little bit, then x minus x naught in this case is negative, which means that the spring force is pushing to the right. I think for most of this, I will just use this because it makes the math a little bit simpler. But just in case you see, if you ever see it written like this, that's what they mean by that. All right, so in this case, suppose we have a spring, a box slams into the spring with some initial velocity, and we would like to know how much the spring compresses when the box comes to rest. Now, if you tried to do force balances, you would get the wrong answer, because force balances, again, are talking about the instantaneous moment when the spring force acting on the force that the box is exerting on the spring. That is different than, say, when what we are asking here, which is that the spring has to do work to suck away the kinetic energy of the box, and we are seeing at what location does the spring finally drain away all the energy of the box. So let's see, I will jump up here. So let's see, so then the force of the spring is then minus kx, comma 0. In this case, it's only acting in the horizontal direction. Similarly, there's only horizontal motion. So the dot product of the two is then minus kx dx. Since it's 1D, I could stop writing, actually, dx dx. I could not write, I don't need to write it as vectors. Actually, that's misleading because the dot product returns a scalar, so I should not have vectors in this final expression. My bad. So this actually, I need to erase this. We're 55 minutes in, I'm starting to get tired. So then the work from the spring is then the integral of the dot product, which is then the integral of minus kx dx. K, the spring constant, is just a constant. I can bring it out. I am integrating over x, and I'm integrating from some initial position, which is where I'm placing the origin, to some final position, which I'll say is xf, x sub f. Notice also in this case that the force is not a constant force, so I could not say work equals force times distance. Because in this case, the force, since it also depends on the position, the force is constantly changing as the position of the box changes. So you could not just use force equal or work equals force times distance in this case. You actually have to do this integral. And this is minus k. The integral of a polynomial, this becomes x squared over 2, evaluated from xf starting at 0. So then this is just minus k xf over 2. And I subtract the same thing, but I plug in 0 for x, so it makes the entire thing 0. So then the work from the spring is this guy right here. And notice k is positive, this thing is squared, so it's positive regardless of what x is, 2 is positive, this is negative, which again makes sense. The object is coming in with some velocity. We are trying to figure out when it has no more velocity or no more kinetic energy, so that kinetic energy has to be drained out of the box. The work better be zero, better be negative in this case. So then by the kinetic energy theorem, the change in the kinetic energy of the box, which has 0 final kinetic energy because it's at rest, minus the initial velocity of the box, or the initial kinetic energy rather of the box with some initial velocity v naught, is equal to the work done on the object, which is negative kx squared over 2. And then you can see that, if I know m, I know the initial velocity, I know k, I can then solve for the final position of how far the spring compresses. If I then ask myself how much work is done when the spring, once the spring is compressed, it wants to push itself back out and stretch back out so that it is not compressed. The spring would rather be in its equilibrium position. That's why there is a force, a restoring force. The spring will push back out, and I could ask how much work does the spring do when it returns to its original equilibrium position? And perhaps unsurprisingly, I'll let you do the math. When you calculate it, it is plus 1/2 k xf squared. So the energy that it took away by doing negative work, it then gives back the identical amount back to the box when the spring returns to its equilibrium position. So what the spring took away, it gave back in the equivalent amount, similar to how gravity did it with the ball. Particularly in the case of gravity and the ball, we also saw that it did not seem to matter what path the ball took to get back to the bottom. All right, last slide, I swear. So the case of the spring and gravity are two examples of forces where what it takes away, you have then the potential to get back. So going back to our analogy of, we had the case of wealth, where we had cash and savings. In the analogy, we had that cash could be put in savings, but you could always get it back by just withdrawing from your savings. That energy, while you did not, or that cash rather, while you did not have it on hand, you had the opportunity or the potential to get it back. And so now we're going to talk about that kinetic energy that gravity and springs are the two examples of forces where whatever energy it takes away, you have the opportunity to get that energy back. So they are examples of forces where we can define something called the potential energy, where whatever energy it takes away or gives back to the object can be interchanged with the kinetic energy of the object itself. So, when is this the case? We say that a force is conservative if the net work done around a closed loop or a path that starts and ends at the same spot is 0. Oops. Equivalently, a conservative force does not depend on the path you take between or from 2 points. Yeah, I guess between is grammatically more correct. Between 2 points in calculating the work done. As an aside, I did not say this in class, but actually there is one more condition that it requires, and that is that a conservative force can only depend on position. It cannot depend on velocity or time, for example. But all our cases, that will be obvious in all the ones that we see in this class. So what do I mean by this? The network done around a closed loop, that might sound odd. We saw this for the case of the ball. In the case of the ball, that I tossed up into the air, it went up into the air to some highest point, and then it came back down to my hand. And in this case, the work that it did was gravity did negative 5 joules of work as it rose up into the air, but as it came back down, it did plus 5 joules of work. So the net work, the work that it did going over the entire loop of the path of where it starts and ends at the same point, the total work done throughout the entire trajectory was 0. Then we also saw that in the case of the ramp, that also was a case where it did plus 5 joules of work. Or when it did, this thing here, it also did plus 5 joules of work. In all those cases, path 1 here, it went up and then came back down. Path 2, it went up, went down the ramp and came back, did the same amount of work. In the third path, it went up, did this weird thing here, and then came back, also did. In all of those cases, the total work was done, both going up and down, was 0. So I actually can sketch a little proof that if I assume that a loop does 0 work, then it does not matter what path you take from point A to point B. So let me do this a little more generally and abstractly. So suppose I have some point A, it might be the ball in my hand, then I have some point B, that might be the ball at its highest point, or this could just be 2 general points where there's some arbitrary force that is acting on the object. We saw in the case of the ball, right, it did one path to get from point A to point B. In that case, the work that was done, if I say WAB is the work done by some force to get from point A to point B. Then there was the return journey, where this is the work done from B going all the way back to A. If I assume that this is 0, a loop does 0 net work, I could also, for example, let's do another color. I could also say, we had the case where I took a different path. It was W going from B to A, 2. But this is also a closed loop here. So by definition, I said that if I assume that a closed path is 0, then this also must be true, and we saw that was indeed the case for the ball with gravity. You can easily convince yourself that if you both of these have a WAB, you could solve this guy for WAB and then plug it into this guy, and the expression that you will get is that WBA equals WBA comma 2. Or for two arbitrary paths, in this case, the yellow path and the red path. For two arbitrary paths, the same work is being done. So another way of saying that is that it does not depend on the path you take to get from point A to point B. And I could have also done this, I could have also did the example where I took some alternative path to get from point A to point B. And I could have written down a similar argument that shows that it does not matter in going from any 2 points what path I take, if it is a conservative force. If it is not a conservative force, then obviously this is not true. An example you could think of is friction. In the case of the ramps, the amount of work that friction does, in the case of the diagonal ramp, is going to be different than the amount of work friction does with this ramp, because the path length that the ball has to travel, versus a steeper ramp, the amount of work that friction does is going to be different in all three of those cases because the path length is different. Some ramps are longer than others, and the amount of work that friction does depends on how much time you spend in contact with the ramp. So in all of those cases, friction would depend on the path you take, and you would get different answers for the amount of work friction does for all three of those ramps. But for things like gravity and springs, you do not. And notice that for gravity and springs, they are two examples of forces where if you take energy away from an object through gravity or springs, you have the potential to get that energy back. And now we can actually write down, and this is the end, don't worry. I ended class just by defining that we can define a potential energy for conservative forces. You can think of conservative forces as ways, you can think of them as savings accounts. In the case of the ball, I threw the ball up in the air, gravity took away 5 joules of kinetic energy. You can think of it in the case, since gravity is a conservative force, that gravity then puts it into savings, and when the ball needed to get that energy back, it could just withdraw from its savings account, and gravity then gave back the same exact amount of 5 joules of energy. So we can define the potential energy for a force as the change in potential energy for a conservative force is equal to negative the work done, where this is negative the work done by the force. And again, all this is saying is that, like in the case of the ball started with 5 joules of kinetic energy. I threw the ball up into the air, and gravity did negative 5 joules of work on the ball. So it took away 5 joules of energy from the ball. And all this definition is saying is you could think then as gravity storing away that energy. So it took 5 joules of energy away from the ball, and as a result, negative 5 joules of energy, gravity then gained 5 joules of energy that it put into savings. So that there's now 5 joules of potential energy that gravity can give back to the ball, in which when the ball then returned back down to the floor, it then gave back that 5 joules of energy. So again, all this is saying is that any energy that a conservative force takes away, it stores up, and then that object has the potential to get it back if it needs it. Similarly, if the object is being acted on by a conservative force and is speeding up, you can think of it as cashing out some of its savings. In that case of the ball coming back down to the ground, gravity did positive work on the ball, so you could think it did positive 5 joules. So you could think of, the negative of that then is negative 5 joules. Gravity, the potential energy of gravity then decreased by 5 joules. 5 joules of energy was taken out of savings and given back to the ball. All right, and that is where we will start up next time.